Thank you for watching this presentation. This presentation is about proximal obstruction to the pulmonary arterial flow, which means obstruction that affect the elastic pulmonary arteries, which are arteries that has rich in elastin and have a lot of recoil. And this part of the proximal circulation is responsible for the conduction of the flow without offering usually resistance. I have had a lot of help on discussing the theory and having the theory being developed. This was initially formulated in 1997. So there are some topics that I will go over. Sorry for being Portuguese. So the idea is to relate the pressure flow relationship with the parabolic function. And the equation, the general equation for a parabolic function on x is y is equal to ax to the square plus b x plus c. But c is the point where the parabola will cross the y-axis. And because we are dealing with a situation that when you have no flow and you have no pressure, so the c is equal to 0 and it will disappear from the equation. So here you have the equation again. Now, when you transform this equation and apply that for the pressure flow relationship, we use the notation as Q for flow. So it is the pressure difference is equal to a constant that multiplies the flow to the square plus another constant that multiplies the flow itself. And this equation is called the Rohrer equation. And these are the notations. So K1 and K2 are constant, Q is flow, and delta P is pressure difference. When this is the Rohrer equation that was formulated in 1915 for the airflow in the airways, and it applies to the flow in general when the flow is non-compressible. So it has two components of the delta P, which is the pressure difference. One component plus the second component. So the first component is derived from kinetic energy of the flow. And this is the Bernoulli principle or the Torricelli principle, which are principles that correlate with the kinetic energy of the flow. And you have the second term that is well known by us, which is the Poiseuille law, where the flow is telescopic and has friction inside the flow laminas. They are concentric lamina like a telescope tube, and this is the second term. And when you look at this Poiseuille term, call attention that you have, it is depend on the viscosity of the fluid, which is in this case the viscosity of the blood. And when you look at the first component, which is the Bernoulli or the kinetic energy component, you have this principle that you have the pressure that is a lateral pressure, so it's a pressure that is a potential energy that's getting the flow without the movement of the flow against the lateral wall. So it's a lateral pressure. And this pressure, the total energy of the system is the pressure plus the kinetic energy. But in this example, the kinetic energy is very small, and most of the flow of the energy is in the form of potential energy, which is the pressure. But then when the flow has to go through a small cross-sectional area, which means this is the point 1 and this is the point 2, so the area in point 2 is smaller than the area in point 1, then you have to have, for the same flow to go through, this flow has to accelerate. And when the flow accelerates, the kinetic energy of the flow has to increase. And from where the kinetic energy comes, it comes from conversion between the pressure, which is potential energy, into the kinetic energy. So as the flow accelerates, then you have a decrease of the pressure at that point. And this term is the term of the kinetic energy of the flow by unit of volume. And you can see that if you divide the cross-sectional area, so if you divide the flow, which is the Q, the flow through the system, through the cross-sectional area, you are going to get the velocity. So a way to describe velocity is divided by getting the ratio between the flow, the actual flow, volume of flow, divided by the cross-sectional area. And because the velocity is to the square, you have the Q to the square and the area to the square. So divide one by the other, it is the velocity, and to the square is the velocity squared. This Greek constant here is specific gravity, and specific gravity means means mass divided by volume. So if you see this term here is the kinetic energy term for solid structure would be m, which is mass, multiplied by v to the square divided by 2. But because this is per volume, so then becomes specific gravity, which is mass divided by volume. And as I mentioned before, this constant, instead of being viscosity, is now is specific gravity. So the whole equation has these two terms, one that is a square term, which is kinetic energy, and the other that is a linear term, which is the Poiseuille law. And because it's adding up both terms, it becomes a hybrid equation. And this hybrid equation can adapt to data of circuits that are laminar, which be getting this component, or I could adapt to orificial flow, which is like a valve or stenosis, that is the kinetic energy. And because it addresses both components, it can adapt to a wide range of situations that I will describe later. And when you look at inside those terms, starting with the Poiseuille law, you can see that the Poiseuille law has a geometric description inside it. So this constant, which is in small case, this is just a converse of unit. That in this case, we could say that you are transforming the metric system into woods or into millimeters of mercury. And this would be the same thing. So this constant that appears here is not really a physical constant, but it is just a unit translation of units. So this is just to give you the dimension correct on your units. But dimension-wise, the geometry of the circuit is the length. If you are talking about a cylinder or a tube, a cylindrical tube, and the cross-sectional area of the tube, and this would give you the geometric description. So when you apply the Poiseuille law to a network of vessels, we are getting this term here that incorporates the geometry, but in a way that's only one number, as it were just one cylinder. So say PVR is 3 woods, you are saying that it corresponds to one cylinder that would have 3 woods of resistance. And I'm saying resistance here because when you multiply the flow by this, you are getting this correspond to the resistance term, which will give you that fraction of pressure. On the same way, when you look at the kinetic energy system, you are also getting one geometric descriptor here, which is a cross-sectional area of flow. And the same way that you can transform a network of vessels into one tube equivalent, you also can transform a cribiform or a multiple hole in a single hole that would have the same behavior. So this term here is describing the behavior of a multiple holes as it were only one hole. And this is a very important point that I want to make here for the theory. So we are saying that you have a descriptor of the geometry of the combined stenosis, the same way that you have a description of geometry of combined microcirculation or distal circulation. And just for notation, this is a funnel-like or hourglass type of a hole that the flow has to accelerate through it and convert pressure into energy. So that's no notation, it's just to highlight a type of a stenotic resistor that is making the pressure to be transformed in kinetic energy. Now, the usual notation for resistance that is coming from electrical circuits, and also we can use for fluid circuits, is this notation, like a zigzag. And but this is just to highlight that they are intrinsically different, as I will going to explore later. And you can assemble those two types of resistors in parallel, meaning that the flow can pass through either a partial flow are competing. So these resistors are competing for the partial flows. Or it can be in series, which means that one resistor is affecting the performance of the other resistance as you have a decrease of energy as it goes through, which is in series. And making that point, I'm calling that a mixed type. And the mixed, those type of resistors that are combined can be recombined in many other configurations, give you a very, very complex circuit. But my point, we are going to see that this whole equation can describe no matter the complexity of the circuit. I will make this point later. So, and why I mean bring this approach? Because if you can fit the data from a patient to the parabolic function, you can extract from that term, which is the kinetic term, you can extract a descriptor, a geometric descriptor that would have a relation to the severity of the disease. So that's the main point of the theory. And one clinical application is that if you are able to get this descriptor, then look at the literature, and I did that in a rough way, rounding things, because there is no data for a parabolic function. So what I assumed is look at the disease like this term would be the most important term. So I'm applying like just a quadratic equation, like y is equal to the a multiplied by x squared. And by doing that and look at the literature, you have two situations. One that is a situation that's chronic, allowing the right ventricle to get hypertrophy and get good performance. And you would have cases of severity. And when this term that you extract from the data come to 0.2 or more centimeters square per body surface area, then it would be just a mild obstruction. And when this term becomes less than 0.1 centimeters per meter square, then it could be severe. Now, if you look at that, comparing to critical areas for aortic or mitral valve stenosis, you are going to see that the critical areas for valve stenosis is in the realm of 0.5, and I'm calling here 0.2 mild above 0.2. So why is that? The reason is that in the valve, the flow is intermittent. It doesn't last for the whole cardiac cycle. So in case of aortic stenosis, have a ventricle behind it. You have a small time for ejection time in the range of 300 milliseconds or less. And with that, all the flow goes through. And for that flow to be able to go through, it will need a cross-sectional area that's larger. Or on the mitral stenosis, it's about the same thing, but you don't have a ventricle behind, but you do have more time for diastole. So then you may have the same critical value, much above 0.2, but you would have a good stenosis, a good flow, and it would be still a patient would be still able to survive. Now, when I'm talking about those numbers here, the difference is that you have a continuous flow during the cardiac cycle, meaning that it lasts throughout the cycle. So that it's not an intermittent flow, it's a continuous flow. Now, when you see these parameters of severity and you compare when it's an acute onset of obstruction, then you see that this parameter becomes less small, becomes more loose because the right ventricle is not prepared to see the afterload. So then those areas is about 50% more. And this is looking at the literature that was published with some data, talking about prognosis or survival. Now, going for the mathematics of the parabola is a curve. A straight line cannot pass through these 3 points. And although I have the data here and here, because the curve or the function has to pass through this point, which is 0, 0, then it has to make a curve. So the first point is 0, 0. The second point is the x-axis is 1, and the y-axis is 17. And this point, the x-axis is 3, and the y-axis is 105. So as you resolve that, this is the solution for the parabolic equation that goes to 0, 0, 1, 4, 17, 3, 105. And this equation can adapt to both circuits that can have a term that's linear or not, because this is the linear term and this is the quadratic term. Now, if you try to accommodate the data with using a straight line approach, which is the PVR type of approach, then you can only pass the line to one of the points because it has to pass to 0, 0. So when you accommodate for the first point, you cannot accommodate for the second. You have to do another line. And if you try to see the performance of the quadratic, which it doesn't have the bx, it has only the ax to the square, it either passes through one point or passes to the other point. So none of those two approaches, the quadratic or the linear, can accommodate for the 3 points very well. And but you can see in this example here that if you see the parabolic approach that has the two types of terms, and you compare with the quadratic one, then the quadratic is pretty close, although it's not perfect. But it could explain the data a little bit. So whenever you have a linear term that's very small, meaning that suppose that you have a stenosis of the branches, but you don't have a lot of distal resistance, then the quadratic and the whole could be very close. So with that principle, I try to accommodate try to foresee what would be those parameters of severity that I described early on, based on applying the data to a quadratic term only, trying to explain the data using this rough approximation. Now, what are the diseases that we have there? The main group is the chronic thromboembolic pulmonary hypertension. And interesting, you can have a situation that is very distal, or you can have a situation. This is very distal, and this is very proximal, and you would have all these classifications that go from 1 to 4, according to the Kenneth-Moser group, UCSD, which is University of California, San Diego. And this is interesting because this classification, this need to address the description on type 1, 2, 3, and 4 is similar to the congenital, to the Frank and Gay classification for arterial stenosis that are congenital. And you see type 1, 2, 3, depending on whether it's more peripheral, type 3, or whether it's more proximal, type 1, or whether it's mixed, which is type 4. Now, this important paper from 1997 from Nakayama, where he described that when you have chronic thromboembolic pulmonary hypertension, just by getting a pressure curve in the pulmonary artery, you would have this wide pulse pressure, and also systolic being high and diastolic being much lower. And if you compare, and this would be like the cardiac cycle, right? The EKG would be running here, which is time, and then your pressure curve in millions of mercury. So, and when you compare a patient with the same systolic pressure, as in his example, you have a systolic pressure, but the diastolic pressure is much higher. So this was the hint for him that he could use when you're doing cardiac catheterization with the catheter within the main pulmonary artery, just by having this discrepancy between a very high systolic and not very high diastolic pressure in the pulmonary artery, you could have a hint that this would be a chronic thromboembolic pulmonary hypertension. And 1 year late, Nakayama did a follow-up study using the echocardiogram with the Doppler data to tell the different diseases. So this one is the chronic thromboembolic pulmonary hypertension, and you see that the estimation of the systolic pressure by acoustic station is giving you in the realm of 50 so millions mercury, 3.6 to the square multiplied by 4, and diastole, the end diastolic pressure being very small, 1.5 to the square is 2.25 multiplied by 4 gives you 9. So it's a very low diastolic pressure. In this other example, when you have a pulmonary hypertension regular case, which could be pulmonary hypertension that's primary or other diseases that are not thromboembolic, then you would have a much higher diastolic pressure. And this is the comparison between primary pulmonary hypertension data regarding the pulse pressure and systolic pressure, the relationship between them, and also looking at the other group. So just to emphasize, I'm putting this arrow showing the discrepancy between the peak velocity and the diastolic peak pressure and diastolic pressure. This case was reported from Brazil, a friend of mine, Eduardo Saad. He published it in this journal and in 1997, and I asked him for the pressure curve. And with that, I vectorized the curve to obtain the coordinates of these curves. And with that, I could digitalize the curve and export it to Excel sheet, and then do calculations of the coordinates of this data to gather more insight on the hemodynamics. So that until that point, we are talking about the chronic thromboembolic pulmonary hypertension. But look at this paper on pulmonary embolism, acute pulmonary embolism, and this is from Morpuk in 1990. And he's describing here also a very peak velocity. So this is the time of the swan guns in the coronary artery, in the coronary unit, intensive coronary unit, and the swan guns catheter with the tip inside the MPA. At that time, it would be a normal thing to do, and in a patient with thromboembolic disease, pulmonary embolism. But the point here that so it's a very precious paper because it's documenting for us that in acute pulmonary embolism, you also have a peak systolic pressure very high and a low diastolic pressure. By the way, Morpuk has trained or had some contact with Kenneth Moser's group regarding this concept of pulmonary hypertension, chronic pulmonary hypertension with high systolic and low diastolic. He used a term here for explaining that the pulmonary artery, the proximal pulmonary artery, which, proximal to the obstruction, would be ventricularized, meaning that it's expressing the hemodynamic of the ventricle. And so the point that I want to make this contrast is that when you have the usual pulmonary hypertension, the disease is in the microcirculation or small muscular pulmonary arteries, which are arteries that are smaller than 1 millimeter of diameter, and until the microcirculation. So the disease is distal, and that's the abnormality. And the larger arteries are not affected by the disease, so they are not offering resistance. You can discuss regarding compliance, but you are not arterial compliance, but you are not having a problem of the vessel offering resistance, increased resistance. And because it affects the microcirculation, this resistance is constant. So what I mean by that is that during the cardiac cycle, you are not changing the resistance of the circulation there, and this is only manageable for medical management with drugs. Now, when you have the proximal obstruction, instead of affecting the distal microcirculation, it's affecting the conductive arteries, which are the elastic artery, which are arteries that are larger than 1 to 3 millimeters of diameter. And in that case, I will make the point that I'm going to make it later, that the resistance, in fact, varies with flow. So as in systole, you have more flow, you have more resistance. In diastole, you have less flow and you have less resistance, which is a contrast from that physiology here. And also, by being proximal, it's amenable, it is at the reach of the surgeon to try to relieve the obstruction. So these are causes of congenital pulmonary arterial stenosis, many diseases, Williams syndrome, allergy disease, and others. And you have also acquired obstruction of the proximal pulmonary arterial flow. I already mentioned the chronic thromboembolic pulmonary hypertension, the acute pulmonary embolism, but you could have mediastinal fibrosis involving the pulmonary arteries and constricting them. And you may have Takayasu and idiopathic isolated pulmonary arteritis, among other causes. So this is a case that I had in Rio de Janeiro. It was a 14-year-old male, that boy, that had a type 3 congenital pulmonary arterial stenosis. And you can see that it's very distal, the stenosis, and you can see different phases of the flow that the capillary phase is not here yet, and so you have a different perfusion of the lung according to the severity of the stenosis. And this is his blood pressure. This blood pressure you can see a systolic being very high and a diastolic being very very low. So we see the systolic pressure is 140, and the diastolic pressure is in the realm of 20 or 25 millimeters mercury. And another thing that I want to call attention is that the decrotic notch, which is the time where the pulmonary valve closes, it is decreased. It is low in the pressure curve, which means that the ejection time is pretty larger. If the decrotic notch were here and the pressure would go down here, I would have less ejection time. And so how can you reconcile that? So when I talked about the chronic thromboembolic embolism, Nakayama, in his description of this typical pressure curve, he called for the compliance of the pulmonary arterial wall of the pulmonary arteries proximally being small, and that's why you would have a high systolic pressure with a low diastolic pressure. But I'm going to offer you a different mechanism. But in order to understand that, the essential points are call attention that the flow through the stenoses to the proximal obstruction are still in phase with the ejection of the right ventricle, meaning that most you have compared to the cardiac cycle, you have a small time for the flow to go through, and most of this flow is going during systole. So what happens is that you have a lot of velocity through those stenosis. And by the way, chronic thromboembolic pulmonary hypertension and congenital pulmonary arterial stenosis and acquired pulmonary arterial stenosis, all of them give you systolic ejection murmur in the back, in the places where you have the arterial stenosis. And another thing that clinically, all of them translate with prolonged ejection time for the right ventricle, which is correlates with the splitting of the second sound in a way that the pulmonary component becomes delayed in comparison, much delayed in comparison to the aortic components. So it's my point is that there is a same hemodynamics syndrome applying to different diseases in etiology. So once you understand that, you accept that most of the flow is passing in a very short time, you understand that you have a lot of kinetic energy. And because the kinetic energy is proportional to the square of the systolic flow, it means that imagine that the flow threefolds, which means that because the kinetic return is to the square, the pressure difference, which requires the proximal pressure to be higher, the gradient would be 3 to the square, which means 9-fold. So you increase the flow by 3 times, and the pressure difference increases by 9 times. And this would result in a very high systolic pressure. And as the flow decreases during diastole, and this flow is provided by the recoil of the pulmonary arteries proximally, and they tend to be hyperpulsatile. And this is a finding that you have on the radioscopy at the time that you do that to put the patient behind the screen, X-rays, and watch the flow. It was described as a pulsatile bed for the congenital pulmonary stenosis. So that flow here would have less velocity along diastole, and that's why your pressure difference drops very quickly, and then you have low systolic pressure. So I'm explaining this flow, this pattern of pressure, not using compliance, but using the kinetic energy through the stenosis, which is a concept that has never been addressed. Now, the point that I want to make to reconcile it's obvious that you can only produce high pressure if the vessel is distended. So at the point that the systolic pressure is going very high, obviously that the vessel is now very distended and becomes less compliant. But the problem in the compliance of the vessel is secondary to the stenosis that is distal to that. So it's an example of a balloon. Imagine that you have a balloon that's leaking, but you are blowing inside the balloon. And because you are blowing much more flow, then the leak can go to the hole, then the flow can go through the leak. Then you are going to inflate the balloon, the walls of the balloon are going to be distended, the balloon is going to be larger, and as you stop or decrease your blowing, or you stop your blowing, which is diastole for the ventricle, then the leak will go and the balloon will decrease and will recoil. So the point is that when the balloon is deflated, the compliance is small of the vessel, but as you blow up the balloon, you stretch the walls and then you produce high pressure, and at that level, the change in volume and compared to the change in pressure becomes in the way of low compliance. But this is secondary, that the runoff through the stenosis or through the leaking of my balloon is smaller than the blowing or the systolic flow that's happening. So it's a secondary decrease of compliance, but not the main mechanism. Now, change now to this case. This case was published by Kozio in 1973, and this is he did that to talk about mediastinal fibrosis changing and causing the splitting of the second heart sound. But so this was a special case because the fibros, the mediastinal fibrosis or the mediastinal fibrosis, it affects the main pulmonary arteries, but has not affected the pulmonary veins. So there was no obstruction the venous side of the pulmonary circulation, and but he did this is a very special case report because and this patient was around 40 years old, and he documented by cardiac catheterization with the catheter in the pulmonary artery and also in the right ventricle. So there was no valve stenosis at all, and you can see that the peak pressures match, and then the decrotic notch is very low, and the diastolic pressure is very low. So it is high systolic with a low diastolic pressure. Here is the aortic pressure, and this is the phonocardiogram, and he's showing here the splitting of the second sound, and which was a wide splitting, and a murmur from the stenosis of the artery, of the pulmonary arteries. Now, and this case is also very interesting because he has exercised the patient. So he brought the patient to the cardiac catheterization lab. He got the data with the patient resting, which is a pulmonary pressure of 74 over 12 with a mean of 33. And then during exercise, the patient went to 128 of systolic pressure over only 21 of diastolic pressure, and the mean pressure has doubled. Okay, and he also did the cardiac index measurements. So it's very interesting here is that the flow went from 2, the cardiac index, to 1.4 times more, which is 2.8. So it 1.4 fold the flow. And I want to call attention because 1.4 is the square root of 2. The square root of 2 is 1.414. So it is, while the mean pressure doubled, the flow through the heart increased by square root of the double, which is 1.4. So it tells us that this has a quadratic relationship more than a linear relationship. And if you think about that, how come you increase much more pressure than increase the flow? If you use the usual PVR approach, you would say that during exercise, the lungs went into vasoconstriction, which doesn't make sense. You increase the flow when you make vasoconstriction because it's completely not physiological. So now, the last thing is to explain and understand the reason for the splitting of the second sound. So imagine here that this peak pressure here is, in fact, is an island. And this A, which is the arterial flow, is like the sea level. So as the sea level drops, the same island becomes larger. So you have the effect of my point is that my sea level here is the pressure in the arterial tree. So if you see, imagine that this is the left side, meaning that this is the aortic pressure, and both ventricles are doing the same pressure, as example. And it takes a time for the left ventricle to open the aortic valve because of the diastolic pressure being high. And then as soon as the pressure in the ventricle decreases, the aortic valve closes and the ejection time becomes that short. Now, when you have the same situation where your diastolic pressure in the pulmonary artery is very low, then what happens is that the right ventricle starts to ejecting, and very soon it opens the valve, and it keeps the valve open as the pressure decreases, and very late would it decrease, close the valve. So if you overlap those two, you're going to see that the ejection time for the right ventricle is going to be much larger than the ejection time for the left ventricle. And this is the reason that you have the splitting. Now, this explanation is in a phonocardiogram book, and for explaining the pulmonic valvular stenosis, why in pulmonic valvular stenosis you have a huge splitting of the second sound. But in this case, I'm using the same explanation to say that because the flow through diastole is small, the stenosis has less gradient. And because of that, the proximal diastolic pressure is low, and then the ventricle is able to keep the valve open longer, despite the fact that the systolic pressure is systemic. And using those data points that I mentioned, 0 for no flow, 2 of cardiac index, and 33 of mean pulmonary pressure, and 2.8 for the cardiac index, and then 65 as the patient exercise, you can see that you can reconcile with a parabolic curve and getting all the 3 points. And if you go by one line, you would calculate the PVR here, and this inclination, this steepness, is going to be less than here, meaning that you have the impression that PVR has increased, and because you are not capturing or considering that the main component that is increasing the resistance is not at the microcirculation, but it is because the kinetic energy of the flow has increased. Now, after that, I went after to see whether in chronic thromboembolic pulmonary hypertension, whether anybody has exercised the patient. Good enough, indeed, in 1990, by Peter Fedulo, he is at the UCSD, which means University of California, San Diego. As I said before, they are the cutting edge in the field. Kenneth Moser was the author who described the chronic thromboembolic pulmonary hypertension study did animal models in dogs and developed the surgery for relieving the obstruction. And they have the best results in the world for the thromboendarterectomy. At that time, in 1990, Peter Fedula was brought into the Congress meeting. The situation that patients that may have not a lot of pulmonary hypertension, very severe, let's say that, but when he exercised, then the vascular resistance would increase and the pressure would go to systemic levels. So the point of these communications was to say that in cases less severe, you may need to exercise the patient to bring about that the severity of the disease is high. There was no awareness of this component of kinetic energy for the stenosis, despite the fact that on Kenneth Moser articles on the group emphasized that you should think about chronic pulmonary hypertension chronic thromboembolic pulmonary hypertension, when you, in the physical exam, you find ejection murmurs and the splitting of the second sound, which is the same findings that you have for congenital stenosis. And having murmur in over the arteries means that you have a high kinetic energy of flow. And this has never been talked about before. So if you put this data here, you see I'm plotting here at rest. And in this case, I calculate from the data the left atrial pressure. And but the point here is that you have these levels of pressure and flow, and he's saying that the PVR has increased, and you can see that a parabola is passing through all the 3 points: the zero, the rest, and the exercise. So my point here is that I don't need to change the geometry of the circuit to explain the data. So here you are thinking that there is vasoconstriction as the patient is exercising, but it's not. This is just the kinetic energy that's increasing from this point to the other. So again, just to in the echocardiogram, when you have those types of proximal obstruction, you would have this is the aortic valve by any mode. You can see the ejection time. Compared to the pulmonary valve at any mode, this time is much longer in the same patient. And here you have the Doppler with the aortic flow through Doppler and the pulmonary flow through Doppler in the same patient. So you see that the ejection time in the pulmonary artery is much longer because the diastolic pressure is much smaller. And now let's go to the congenital, because for now, until now, I said quiet, right? I mean, although I have shown that case of the 14 years old. But in this case, it's a review, the first time that it was brought about, that when you have a bilateral stenosis of the primary pulmonary arterial branch, means the left and right, you would have that characteristic curve with a high systolic and a low diastolic. And they would talk about, when they say that this was a ventricularization of the pulmonary MPA pressure curve, which is the same notation that Morpurg has said for pulmonary embolism. And this is a comparison with normal subjects. But the point here is that later on, they published 84 cases showing that no matter where the stenosis is, whether it's proximal stenosis or whether it's in the main pulmonary branches or more peripheral, in the 84 cases, they always found a very high systolic with a very low diastolic, and they call attention also for the low diastolic dicrotic notch that I have already explained why. So This is interesting. Another thing that I don't have here is that in the past, before having Doppler and having even echocardiogram available, when you would do pulmonary arterial band for patients with VSG, there is a publication showing that when they would know that the pulmonary arterial band was effective without doing cardiac catheterization by measuring the splitting of the second sound. And when the splitting would be more than 40 milliseconds, then it would mean that the pulmonary arterial band was stenotic enough to protect the lungs. So everything comes about, no matter whether you have acquired by the surgeon put a pulmonary arterial band, or whether it was a chronic thromboembolic type of problem, whether it was an acute embolism, or whether it was congenital, you always have this syndrome of a high systolic and low diastolic pressure. Okay, now, in this case that I had in Rio, this 14 years old boy, I had, in blue, you have the true data in blue, with a high systolic and a low diastolic pressure. Then what I did a square root of this pressure curve, keeping the mean pressure of the curve equal to the mean pressure of the original data. So what I have in this scale of the thing, but I'm taking away the quadratic relationship. It's like that obstruction is not proportional to from the blue that the obstruction is proportional to the kinetic energy. I just take away the quadratic correlation, like transforming that as a similar curve that would have a similar severity of stenosis, but instead of being proximal, become distal. And as you see, after I do the quadratic transformation, this pressure curve is much more similar to a pulmonary arterial trace that is in the pulmonary hypertension, idiopathic pulmonary hypertension. This is just a theoretical approach, just to show how distorted this curve becomes because of the kinetic energy. Now, if you divide that curve that's already did the quadratic, and you divide that by a factor that brings the mean arterial pressure to normal levels, which is like in the 15, then you would have a pressure curve that looks very much like a normal patient curve. And remember that the flow and pressure, they are, when you have a laminar regime like Poiseuille, they are proportional. Then when you see that, you can thinking of the pressure of the flow going. You are seeing a pressure curve, but you can think that the flow is going that way. And all of this is just a guessing work, right? It's just like trying to extrapolate from the data that is the true data is the blue. Everything else is mathematical manipulation. So, but using that mathematical and getting what would be the velocity of the flow through the stenosis and see doing this calculation and doing this VTI, which is velocity time integral, to tell you how much flow, how much distance the flow went through, like the VTI, then you can have an idea of how much flow passes during systole and during diastole. And by that, despite the fact that the systole lasts much shorter than the diastole, you have more flow in systole than have in diastole, theoretically speaking, because as I said, everything here is mathematical calculation. I also did that curve with Eduardo Saad, my friends, that published that paper. I digitalized it and also got those partials. And you keep seeing that the systolic flow is more than diastole, but keep in mind that the duration of systole is much smaller than the duration of diastole. So I have much more flow velocity in that. In this patient, it was a female adult that was in frank heart failure. So probably if the right ventricle would be more healthier, we would have much higher systolic pressure and probably less higher diastolic pressure. But this is regardless of patient have heart failure. So I suggest that you take a break. And from this point, I would like to uh, get the study that I did in vitro, and the goal of this study was to challenge the Rohrer equation, which is the parabolic, to see whether it could adapt and fit to the data of obstruction that are very challenging to believe that it could adapt. So I'm going to show it from now on, this part of the presentation. So what I did, I went to the flow lab here at the UC Denver with orientation of Kendall Hunter, and we did arms on the circuit that have a linear behavior, like Poisson law, and then nonlinear, which is more like a stenosis. And we would study that with a steady flow situation, and then put a Harvard heart pump simulator to reproduce the pulsatile flow conditions. And we got the data time average and also instantaneous measurements. So here is the type of resistors that I used. So for the nonlinear resistor, when I say nonlinear, I want to call attention that these are resistor that has high kinetic energy. And you see the Venturi, which is a very predictable one. You can relate the geometry with the behavior very easily. But I also challenge, so have more tight or less tight, but I also challenge that by using a very chaotic type of obstruction. I put those corks, the wine corks, inside the tube, and you see that it's very difficult to describe the geometry of the spacing through them, and imagine even more the geometry of the flow that's going through. And then I put those corks, also another resistance is the corks set apart to even emulate more distal stenosis in series, not distal, stenosis in series. And then in between the corks, I put pebbles inside. So you can imagine how many pathways a flow has and how difficult it would be to describe that mathematically and correlate to the flow and predict the behavior of the flow. And then another one that I have foam, in black is a foam in the middle of all this. So the foam tends to bring viscosity to the configuration. So it's an internal mixed resistor here that has high kinetic energy and also some visco resistance being brought apart. And to go even more crazy, I did that many times with cork and foams and even cork inside, and to try to challenge a lot the parabolic description of the Rohrer equation to fit the data. Now, on the branch that I would need to have a laminar type of flow, I borrow the Darcy law concept, which is a law that describes flow through porous medium. So inside this sewage tube here, I put foam. I try other fillings, even pebbles, but it will give you very little resistance. So I use different density, specific density of foams, different foams to build up different resistors. And then I would test those resistors individually, and then I also test them in parallel to address the global behavior of the circuit and see whether the Rohrer equation or the parabolic flow would fit. So here we have the data and the true data of the points. So these are the points of flow and pressure difference. You see that it goes to 150 of pressure difference from 0 to 150 in this case, and the flow went to 0 to 2.1 liters per minute. And you see that the data is plotted as a dot, a black dot, and you see that the parabolic regression has a very good fitting to the data. While if you do the ratio approach, you have to do for every point a different ratio, which is crazy, right? Or if you try to get all the data together, this would be a regression that goes apart from the vertical line from the dot towards the blue is going to be the error that you have. And if you try to approach with only with a quadratic regression analysis, you would have a little bit better maybe, but there's still a lot of error. And this resistor here is the one that I'm talking about with a lot of visceral forces inside it. So this is the lab for the steady flow study. So the resistance is here, one resistor. Then I put like a lot of resistors in parallel. But this it would be you have a pump that would pump the flow with water with glycerol, which with the same specific gravity of the blood. Same viscosity of the blood, and then it would have like a kind of a waterfall here to keep the height of the fluid all the same, and from that height you would have another tube that would go through the resistor, and then it would be collected in the chamber which has the same type of waterfall. By that way, the pressure difference would be dictated by the level of this surface of fluid column to this fluid column. This would be the pressure difference, and I could change the height and then do different points. Another thing just is that I used large tubes to make sure that I would not have resistance through these tubes. The Reynolds numbers here will be very small, because despite the fact that the Reynolds number increases with the tube diameter, it also decreases with the velocity, with the square of velocity. With the velocity, but the velocity decreases with the square of the diameter. So by using large tubes, I was in fact decreasing the Reynolds number, because the cross-sectional area will increase to the square of the diameter, and the velocity would decrease with the square of the diameter. And to give you an idea, to generate even higher pressure, I had to open a window on the top, on the ceiling, and put the chamber even above the level that it is here to generate high pressure. So then this diagram of the circuit, where it could behave as a column drop, steady flow, and or having a pulsatile blood pump of Harvard, and in the outlet I would put a chamber to emulate the elasticity of the artery. It would be air and fluid, and as the pump pumps in, it generates a pressure that compresses this air, and the coil effect of this compression would emulate the recoil of the artery. And then I would have this chamber here. From there would go the arms, and these three arms here would be the arms that I would connect the resistors. It could be venturi, could be the corks, and I could change them, right? And the other arm, so these are in parallel, the other arm would be a linear resistor. And then we would get here two outlets in order we could measure the partial flows, but these outlets would have the same height to make sure that the pressure inside here would be the same as the outlet pressure. on both branches. And these are the notation for faucets that you could select the arms or not. And this is the schema of what I just showed. And this is an example of the data emulated with pulsatile flow. And this is what would correspond to the MPA. Would have a catheter inside that chamber, and then a catheter in the outlet chamber, emulating the left atrium, and this is emulating the main pulmonary artery. And then I would have a transducer of measuring the flow that's going through instantaneously. And despite that, I would collect the flow in the bucket after 1 minute, and then measure that flow, that volume, to make sure that I was getting the data. So here I have three types of resistors: the linear resistor, which is the foam that was borrowed from Darcy law that emulates the Poiseuille law, and you have the Venturi, which is the perfect obstruction, ideal, and then the very complex. And I did that for everyone. And with that, I would use the parabolic regression. You see that those dots are the true data, and you see the parabolic fitting very well. And because it's a linear resistor, you use the racial regression, and it's not as perfect. Now, what I want to say here is a small detail, important detail for you maybe. In the beginning, you see this very straight, and after some point it starts to bend. What's happening here is that the Darcy law has the same behavior of the Poiseuille law, but when you force the flow very much, you start having kinetic energy inside the flow, despite it being a foam. And then it starts to behave, you have to use the Forsheim equation. And the Forsheim equation is the same equation as the parabolic equation. So that's why the parabolic is fitting very well, because no matter what it is, it will fit. And then the Venturi here, which is this one, very quadratic. And you see that the parabolic is right on the dots, while the quadratic is a little bit off, but very good, because it's a very perfect type of orifice. And when you have the corks, then you have more viscosity in that. So you see that this dot that across the parabolic function can fit very well. And the quadratic is very close, but not very good. And so as good. And then we did that for many resistors. I construct one that will be equivalent of 2.6 wood, same type of stuff. One that's 6.4 woods, the other one 7.9 woods, the other one 27.8, meaning that could be just a segment of the lung. It's very, very high resistance. And the kinetic resistance, again, showing the data. And then you go from all this. And so all of those circuits, I did the regression analysis. If you pay attention, the parabola is always there on the dots, which are the true data. So this is how many runs I'm getting data through. Six configurations with mixed arms, pulsatile or not pulsatile. And when it was pulsatile, I did with a high compliance emulation or low compliance emulation, depending on how much air I allowed in that compression chamber after the heart pump, and the outlet of heart pump. And then we have all these runs, and these runs generated 385 data points altogether, pulled all together. Now, I want to address this lower part of the schema. This is for linear resistor, the foam resistor that I constructed. So if you put a lot of air inside the compression chamber, it will work with a lot of elasticity. So it will dump the systole and diastole, although the flow is being pulsatile, alternated, like the heart is. with the Harvard heart pump emulator. And if I decrease the amount of air to be compressed, it becomes more rigid. And by that, I have a high systolic and low diastolic. So in spite of this flow being laminar or being linear, it's the point that you can alter the compliance of the artery and making a high systolic and low diastolic is well taken. It's not a new thing, right? But what I'm saying is that I'm explaining much more because of the kinetic energy than because the compliance is different. Now, on the Venturi, which is pretty kinetic energy flow type of flow, then you would have, if I use a lot of compliance, then I can emulate even normal curves, despite the fact that the flow is kind of kinetic energy. But I have a lot of flow during systole and diastole here, right? And so when you use low compliance, then you elicit that upper and high upper and low, but remembering that you have a high flow in systole and low flow in diastole here. So the flow regime in here have much more kinetic energy here than it was having here, and so that would be the study of the compliance affecting. Now, when you do a regression to fit the data, I have like a set of suppose 10 dots, 10 points, measuring points. I fit the equation, and then I reproduce based on the flow that was entered for the equation. I reproduce to see what the equation would give to recover the data that we measured. So that's the measured flow, the true pressure difference, and that's the flow, that's the pressure difference, that was measured for each flow, and then that is the predicted pressure difference based on the regression equation. And I put all of them together, and you can see that the line that has they are equal is y equal to x. Y equals to x. This line is the 45 degree, the tangent of 1, right? The tangent of 45 is 1, and then this is the green line. So the dot from the equation, from the regression equation, if it is good, it has to drop over the green line. And if it is getting an error, and the error will be measured vertically, then it would be away from the green line. So in black, this is the combo equation, which is combo from combining the linear and square, which means the parabolic equation or the Rohrer equation. And you see that the black is right on the green. And when you have the square, you would have some errors. And if you have the linear, for non-linear resistor has high kinetic energy, I have more error. Now I can also plot, instead of plotting the predicted pressure, I can plot just the error in comparison to the true pressure difference. So what was the error for that pressure difference after the regression equations for the 3 regression equations? So the same data here. You can see that if the error, so my green line now becomes my 0 line, and you can see that the black is over the low line. The most error, the highest error was like 3 millimeters mercury, and it is over a range that can be from 0 to 200. 3 millimeters mercury is very good. And as you do the linear, so this sinus appearance is kind of amplified because now my scale of error is 40 instead of being 200. So this kind of amplified, and we can see how the regressions, the very good regression was the parabolic regression. And then we can, I did that for many analyses. Here, 273 points. And then for all the 385 points, you can see that here it's called the polynomial approach, which is the combo approach, which is the what's the name, the parabolic approach. So you see how in the target there's no dot outside that point. And here for the arrow is the same thing, because these graphs correspond to these graphs here. This is the arrow graph, the Blend-Altman plot, and the linear approach would have this type of arrow, and the square approach would be this type of arrow. You can see that one is symmetrical to the other because this is the true and this is the aberrant view from the square, quadratic, or the linear, which is a ratio approach. So the point here is to say that we challenge very much the combo equation or the parabolic equation to fit the data, and no matter what I did, it always fit very well. So I'm very confident that this data can be applied to human animals, to biology. And so another thing is when you have that concept that you have a branch, you may have like a segment that of the lungs, or a couple of segments or few segments that's not protected by stenosis. So the pathway through them is going to be a laminar flow type of path, a linear behavior. And in the other segments, we have stenosis. So how do they behave when you have the same pressure going through them and arrive to the same atrium? So you would expect this phenomenon of flow redistribution. So you have in this triangle a linear arm, and you see that the flow increases, or the pressure increases as the flow goes through. And on the nonlinear arm, which has the stenosis of the arteries, you would have a flow increase less than the pressure increase, becomes steeper and steeper, which means that at high pressure, I have more flow at high pressure. If I put a horizontal line here, at 9, suppose, about 9 here, I would have more flow through the linear arms than I have through the stenostic arms, which means that at high systolic pressure, the unprotected segments are suffering a lot. The microcirculation would suffer a lot. And if you see a relative ratio of contribution as the flow increases or the pressure increases, the flow will increase. But the relative between them is going towards that the more pressure you develop, more flow, more contribution you have by the linear arms, which means they are being burned out. And this is a mixer circuit, again, doing the same type of example. And this was the theoretical approach before I did the study. I had that hypothesis. And I'm putting, as an example, this is the theoretical situation, and with the same data that I was showing you, but now the slide is, the pressure is down and the flow ratio is up, is in the y-axis. But the point here is that at the high systolic, so this is the flow going from diastole towards systole, the pressure, and as the pressure goes up, you have more contribution of the visco flow to the circulation, to amount of flow, and when the pressure goes down, then you may have more contribution of the kinetic flow. So it's like a selective approach. So another step that's a clinical relevance is how to extract, when you have a chronic thromboembolic hypertension, you may have a distal disease that's very important, and then doing surgery to relieve the proximal obstruction may be harmful to the patient. So how can we extract the importance of the proximal obstruction as opposed to the distal vascular resistance. So, and this approach allows us to figure out a way to do that. So let's start from the Rohrer equation again. Pressure is proportional to the square of the flow plus proportional to the flow. If you divide both sides of the equation by the same quantity, which is the flow, this delta P by Q corresponds to resistance. And this term here is going to be the resistance, but here this term becomes a resistance that's proportional to the flow. If you double the flow, you double the resistance. Plus this term, which is the Poiseuille term. When you divide by flow, then you have just the Poiseuille resistance as we know. So because the resistance that you measure, if you do just the calculation, it's in fact not the true resistance, because the resistance that's inherent to the diameter of the vessel, that's distal, is this Poiseuille term, which is the resistance. But this one increases with the flow. So I coined this term of apparent resistance to bring attention that what you measure as apparent resistance is going to be depend on flow and not a true description of severity of disease. We have to go inside this term here to figure out the area of the combined area of the vessels that are stenotic. Okay, so when you do that, you divide that. What you will have is this for this now because this mathematically becomes y equal to ax plus b, which is a straight line. So here we have the straight line. In this data, as published by Peter Fedulo, you see that these lines point to the 0, 0, which means that this is kind of a equation that is a parabolic, a quadratic relationship. So how do you do that? So this explain again. The concept, imagine that you have a point here, and you said that your PVR is that much. And then you have another point here, and you say that the PVR is that point. So this PVR is in fact an apparent PVR, because the difference between them is the kinetic energy of the flow that is translating as increasing resistance. So when you transform this equation, divide by x on both sides, you get a new y, because now y here is pressure and y here is resistance in Woods. And then you have the equation that becomes a line, a straight line. And the point where the line crosses the y-axis is your B point. This B point corresponds to your resistance, your distal resistance. And this is the part that's dependent on flow, which is the part that's proportional to the flow, which is kinetic energy, in this example. So let's see that. So let's get this data from Peter Fedulo. You see what he's calling the increase of resistance. Then we pass the parabola. And here are the equation, a mathematical notation, calling attention that is crossing the zero, because there's no flow at the zero line. And then the concept here is that this is the visco resistance, which is constant, mostly in the microcirculation. And you have then the stenosis, and this is a resistance that is proportional to flow. And then when you transform this data, divide the equation by flow on both sides, you get now resistance. So we are transforming pressure into resistance. And now you have the data here. That was the step that we did. So again, that's the way that we got to that point. And this is the data. And one thing to call attention is that here, while the flow in this patient from rest to exercise on this group of patients increased 1.29, the the amount of increase on pressure has increased to 1.9 to the square. Now, if you put on the resistance domain, flow to resistance, when the flow increases 1.29, the resistance increases 1.29. The reason to be so equal is because this line is crossing the zero. It was the data that he published, not me putting that. Now, let's see a theoretical example that this line will not cross the zero. So I would have a B point here that's different from zero. It's 400 here. So the steepness of this line is giving you the variation of resistance by flow. Delta Y divided by delta X gives you the resistance, the variation, the steepness of the tangent of the graphic, or the A. So in this case, it gives you 120. Now, the point that's crossing the line is if you don't have that component, as you increase the flow, the resistance will stay the same. So this would be your distal vascular resistance, the resistance that's not dependent on flow. And in this situation here, my 400 is my this is in delta P, not in here is resistance. But this would be your resistance of 400 multiplied the flow to give you pressure. And this is going to be 120 multiplied by the square of flow to give you the other component of the pressure that is going up there. And if you do that and you divide by 80, you convert into Wood units, the resistance into Wood units. And so what I'm saying in this approach is that whatever is in pink here is what the surgeon can do by taking away the resistance based on this data. Now, it may be that inside the arterial stenosis, it can be so complex. Maybe it has a long segment of stenosis. That despite being inside the stenosis, I'm seeing it as a distal resistance. But the point is that I promise that when the surgeon will be successfully efficient by taking away of the resistance, that I should bring that to 400. But if inside the stenosis I still have some linear components, it can be even better. And in this more light blue, we have the true distal vascular bed. And how would I get the line? I need 2 points, right? I need at rest and at exercise. And then I will have epsilon equal to AX plus B. And the B would be the resistance as I put here on 400. Now, suppose that now you do the cast, the patient is at rest, and then then you exercise him. You got that other point, and then you give a vasodilator. Theoretically, this line would go in parallel, so you only need one situation of vasodilation, and you plot a parallel line, and you're going to get a new B point, which means a new distal resistance. So this would be the vasodilation effect that you gave oxygen or whatever you gave for the patient, nitric oxide, etc. So, but it doesn't. You may even do the vasodilator and get the patient to rest and exercise. Make sure that these lines are in parallel. But the point that I want to make is that you not only can address the steepness, which means how much stenosis can be relieved, how much of the surgeon will help the patient, and you can even see the vasodilation that you may have in the distal bed. So imagine that I have a curve that's very flat and here very, very horizontal and with a lot of resistance. So the surgeon should not do anything, because if he goes there, the patient will come out with a high resistance. So, and this pretty much the obstruction, the theory. This is just to address that thing about the ejection time. We could use that in echo to try to figure out a patient that comes in with pulmonary hypertension. If you have an ejection time that's much larger on the right ventricle than it is on the left, you should think about chronic thromboembolic pulmonary hypertension. Now, this is the kind of summary of what I was talking about. And these are some important papers that help us to understand the disease.